Hello everyone, welcome all. In last videos, we are discussed about the elimination reactions, E1 elimination and E2 elimination reactions with mechanism. In this video, I am going to discuss about some stereochemical aspects of E2 elimination. In the last video, that is E2 elimination reactions, bimolecular elimination reactions. In that video, I also mentioned some stereochemical aspects, and this video is the continuation of that video, and some other stereochemistry of E2 elimination is discussed in this video. Okay, let's start with the stereospecifity. Okay, what is stereospecifity? We can say that the E2 elimination reactions are stereospecific. So what is stereospecific reactions? Okay, the stereospecific reactions in which the stereochemistry of the product is determined by the stereochemistry of the reactants or the starting material. For example, we are going to check the stereospecificity of E2 reactions by taking an example. Meso 1,2-dibromo 1,2-diphenyl ethane. This is the compound. Okay, we are first taking the meso form of this compound, and the isomer will be like this. This is the meso compound. By Srereospecifity projection, the compound is like this. H, here H, then pH, Br. This is the meso form of 1,2-dibromo 1,2-diphenyl ethane, and it undergo E2 elimination reaction. That means minus HBr is an anti-elimination. H and Br here, and it's an anti-elimination, and the product will be an alkene with this eliminates, and like this pH and Br. You know that this is an alkene with a cis configuration. Okay, this is an alkene with a cis configuration. Similarly, we are checking plus or minus 1,2-dibromo 1,2-diphenyl ethane. Okay, that will be the Srereospecifity projection will be like this. Br, H, pH, and H, Br, pH. Or another form, plus or minus form or DL form, another form is like this. Br, pH here, phenyl group, H here, Br here H, and here pH. These are DL forms, DL form isomer, and it undergo E2 elimination reaction. That means minus HBr, H and Br anti to each other here also. Here the two compounds give the same product. The product will be like this when it eliminates H and pH, and here in this part pH and Br. You can see that it is a trans compound. This trans compound. Both this compound give the trans product. This compound also eliminates HBr and gives the same product like this. So we can conclude that the E2 reactions are stereospecific. This when we take the meso form of this compound, it gives the cis product. If it take plus or minus form or DL form, it gives the trans product. That is why we can say that E2 reactions are stereospecific. Next example, we are going to take the elimination reaction or the reaction of Ki potassium iodide with a 2,3-dibromobutane. Okay, from 2,3-dibromobutane. Okay, reaction with the Ki, and Ki is an E2 elimination reaction, and 2,3-dibromobutane is like this. Br, CH3, CH, CH, CH. This 2,3-dibromobutane reaction with Ki, it gives you alkenes by elimination product by eliminating the 2Br. These are anti-eliminations. 2Br minus Br2 gives Br2 eliminates and gives the product an alkene, and we are checking the stereochemical aspects or the stereospecificity of that reaction. For first, that we are taking the meso compound. Meso 2,3-dibromobutane is like this. Meso 2,3-dibromobutane is like this. Br, CH3, CH3, H, and by rotation of the groups in this carbon, it is equivalent to Br, H, CH3, and by rotating 120 degree, Br comes here and H, CH3. Okay, so this Br and this Br are anti to each other. Elimination occurs by reaction with the Ki, and minus Br2 eliminates and form an alkene. Okay, so what is the configuration of this alkene? This Br eliminates, H is here, CH3 is here, then here this Br eliminates, CH3 is here, H is here. Okay, we can check this is with a trans configuration. This is a trans compound. So trans 2-butene is the product here. The point is when meso form reacts with the Ki, it gives you this trans form. And what about DL form? This is the DL form here. This will be like this. Okay, this is the here Br, CH3, H, and here it will be like this, CH3H. This is one form, or another form, Br, H, CH3, here CH3H. These are two forms, DL forms, plus or minus forms. Here Br, and similarly elimination takes place from these two compounds, any of these compounds, minus Br2. What will be the product? We are getting an alkene with the configuration. We are checking this Br goes out, and H here, CH3 here, and here this Br goes out and H is here, CH3 is here. We can see that this is a cis product with a cis configuration, and this compound also gives CH3H and CH3H. This also gives a compound on elimination with the Br2 is with a compound with a cis configuration. That means this compound 2,3-dibromobutane on reaction with the Ki is a stereospecific reaction. The meso form gives trans product and the DL form gives the cis product. Another example for stereospecificity is taking an example, one diastereoisomer of this compound. This is a compound, two phenyl groups, CH3, Br. This is the one diastereoisomer of this compound. It's on reaction with NaOH, say base. It gives you an alkene with a E configuration. That means pH, CH3, pH, H. Okay, this is with E. That means this is the higher priority group 1, 2. Here also 1, 2. This is the higher priority groups in opposite. So is E alkene. This will be an E alkene. Okay, this is the product. E alkene is the product when we taking this diastereoisomer. Now we are going to check the details of this reaction. Redraw this compound like this. Redraw this compound. We can redraw this compound like this. This here CH3, CH3 like this, CH3, and this is pH comes like this, and H. Okay, here Br is opposite to this one, and pH like this, in the last this one is H. Okay, we can redraw this compound like this, and this on elimination of HBr, that means OH minus attacks here, it goes like this and this goes out, minus HBr E2 elimination reaction, it gives you the E alkene. And for more details, we can draw the Newman or Soho's projection of this compound. This Newman projection is like this. Here Br, H, and in the next here pH, and here the pH, and CH3 and H. Here the CH3 and here is the H. And it on elimination, this H and Br are opposite, anti to each other, they are eliminates and gives the alkene like this, pH and H, E alkene will be the product. You will get the product like this. So this diastereoisomer of this compound gives the E alkene. Next, we are taking another diastereoisomer of this compound and check whether it is E or Z. Another diastereoisomer of that compound is this one, CH3 PH Br. This one reaction with the NaOH gives a product alkene like this, that is CH3 PH H. You can see that it is a Z alkene. So this diastereoisomer gives the Z alkene. Like the previous one, we can redraw this one like this. CH3, here is the H, here is the Br, HBr, here is the pH, and here is the H. Here is the pH and here is the H. This on minus HBr E2 elimination, that means this H and this Br eliminates, gives you this Z alkene. And we can draw the Newman projection of this compound is like this. Here Br opposite H, and here pH opposite H, and here pH opposite CH3. This on elimination HBr, it gives you this product like this. That means a Z alkene, a double bond, same side, the pH in same side, and H and CH3 on another side. This will be the product here, Z alkene. So stereospecificity of this reaction can be summarized like this. This is one of the diastereoisomer of this compound. We can redraw this compound like this, and the Newman projection of that compound is like this, which undergo NaOH reaction with NaOH, or it undergo E2 elimination reaction. That means this HBr eliminates and gives the product E alkene as the product. Okay, another diastereoisomer of the same compound, we can redraw like this, and this is the Newman projection of this compound. Minus HBr, that is E2 elimination, gives a Z alkene as the product. Okay, so this is a proof for the stereospecificity of the E2 reactions. And here you can see in this Newman projection, the two bulkier groups in this reaction, two bulkier groups in this diastereoisomer, two bulkier groups are in the same side, or they are synclinal. Okay, synclinal, or in Gaussian conformation, so it is little bit unstable. So this this compound, this conformation is adapted by a relatively small proportion of molecules. Okay, because of this Gaussian conformation, the large number of molecules will adopt the conformation this one because it is a stable conformation. Here the bulkier groups are in opposite directions, but here two bulkier pH phenyl groups in synclinal, so it is little bit unstable and the molecules are relatively smaller proportion. This conformation, the molecules with this conformation is very little or very small proportions. So the major product or the reaction, this reaction is more than 10 times. This 10 times faster than this first reaction, second reaction. First reaction is 10 times faster than the second because of this interaction here. So this is the fastest reaction and this is the slowest reaction. Anyway, E2 reactions are stereospecific. We can justify it through the examples that we are already discussed. Next, I am going to give you one example, another example for regioselectivity in E2 reactions. In the previous video, I already give you one more than one example for regioselectivity, and another example for regioselectivity is like this: regioselectivity in E2 reactions. Okay, we know that E2 reactions gives generally gives more substituted products, but when the base is bulkier base, it gives less substituted products. For example, this is the compound. This is the compound. On reaction with H3PO4 at 120 degree Celsius gives the product like this. This will be the product. So is a more substituted alkene is the product here. Another example, this compound is on reaction with a bulkier base like potassium salt of, this is thrice, ethyl thrice. This gives the product like this. Here the less substituted product is the major product, and this is the regioselectivity. Okay, this base is like this: C, an ethyl group, second ethyl group, there is a third ethyl group, and O minus K plus. So it is a bulkier base, and bulkier base gives you a less substituted product as the major product. We can check why this happens. The explanation of this observation is, okay, the reaction is like this: Cl CH3 on reaction with the KO CET thrice ethyl group give the product like this. This will be the major product. The explanation of this observation is, this is a cyclohexyl ring. This is a cyclohexyl ring. Okay, and here and one Cl and CH3. Okay, bulkier groups are always in equatorial position, and when it attacks by E2 mechanism like this, OH minus attacks and this bond goes like this. This is the usual mechanism that we expect, and when this happens, the product will be more substituted product, and if it happens, the product will be like this. Okay, more substituted product. But here this does not observe. Here what happened is, here this one cyclohexyl ring, Cl C H H H, here is also H. This, or here also an anti-hydrogen is here, both positions to Cl. Here these two are ring hydrogens which are more hindered to the bulkier base, that is this base, this bulkier base. These hydrogens are more hindered. And here what reaction takes place? For this Cl, here is an anti-hydrogen in this CH3 group, and it eliminates this base abstract this proton, and bond goes like this, and this goes out, and the product will be like this. Here is a double bond forms that is similar to this one. Okay, and in the cyclohexyl ring, these hydrogens are more hindered to this base. So if from the CH3 group, one of the hydrogen eliminates with the, and Cl eliminates, and the product will be less substituted product. It is another example for regioselectivity in E2 reactions. And here this methyl hydrogens are more accessible to this base than this one. These are hindered, these hydrogens are hindered, and these hydrogens are more accessible to this base. So this observation occurs, and this will be the product, the less substituted product will be the product, major product. So that's the regioselectivity of E2 reactions. Another example is compound on reaction with a base undergo E2 elimination and gives two products. Two possible products are there. This is more substituted products, and this is less substituted product. And you can see the observation when this sodium methoxide NaOET is used, 69% of this product is like this, more substituted product, and here 31% is only this one. This is minor and this is the major. When the tertiary butyl alcohol and the sodium potassium salt of tertiary butyl alcohol is used as the base, this is a bulkier base, only 28% of this more substituted product is formed, and 72% of this less substituted product is formed. So this observation, this compound, the elimination of this compound and this observation gives the proof for the regioselectivity in E2 reaction when the size or the bulkiness of the base increases. Next, we are going to discuss about the E2 eliminations in cyclohexane ring. Okay, we are familiar with cyclohexane ring. This is a cyclohexane ring. Most stable conformation of this one is the chair form. This is the chair conformation of cyclohexane ring. If it is a substituted cyclohexane like this X, okay, and this will be the more stable conformation. The X, the substituent should be in equatorial position for the most stable conformation. Here is a substituent in equatorial position. So when it undergo E2 elimination reaction with a base, okay, we have a condition for this eliminating group. Okay, there should be a anti-periplanar or trans or anti-periplanar H or hydrogen should be here. The presence of the anti-periplanar hydrogen promotes the E2 elimination. But here, this to this bond, only this CC bonds are anti, that is anti-periplanar, only these CC bonds. No hydrogens which are anti-periplanar to this one. So you can check, these are the hydrogens which is in the next carbon. These are the hydrogens, but none of these hydrogens are anti to this one. For here elimination to occur, the ring should flip and form by ring flipping. Okay, this one, X goes here equatorial position becomes to axial positions, H, H, H and H. So and then here H minus or the base one comes, this hydrogen and this eliminating groups are anti to each other, or this hydrogen and this X or the eliminating groups or the leaving groups are in anti to each other. So the base can abstract one of the hydrogen like this goes like this, and this goes out, and the product will be a cyclohexene will be the product. And one of the conditions for elimination to occur in cyclohexane ring, that the eliminating groups, and that means the X and the H hydrogen should be in anti to each other or trans to each other, or they should be anti-periplanar to each other. And also for in this cyclohexane ring, for to be they are in anti-periplanar, they should be in axial positions. The eliminating group should be in axial positions. Now we are going to take two diastereoisomers of cyclohexyl chlorides. Okay, cyclohexyl chlorides. This is the two diastereoisomer. One is CH3 chlorine, and this is the isopropyl group, bulkier group. This is called neomethyl chloride. Neomethyl chloride. And another one is like this, CH3 Cl, and here isopropyl group. This is methyl chloride. Methyl chloride. So two diastereoisomers of cyclohexyl chlorides, neomethyl chloride and methyl chloride, each one reaction with a base NaOH, sodium ethoxide. It gives product like this. This is the one of the product. Plus another chance for this undergo E2 elimination is like this, and this is in the ratio 3:1. This is the major product and this is the minor product. When it undergo E2 elimination reaction, it gives only one product. The product will be like this, CH3, this one, isopropyl group. So this is the only product, and this reaction is almost 250 times faster than this one. Okay, this reaction is 250 times faster than this one. We are going to explain why this happens. Okay, so neomethyl chloride gives two products. This is the most substituted alkene and this is the less substituted alkene in the ratio 3:1, and here this methyl chloride gives the only one product, and this reaction is much slower. That means about 250 times slower than this one. Why this happens? We are going to check why this happens. First, neomethyl chloride. This is the neomethyl chloride. This is the CH3 Cl and isopropyl group. This is equivalent to, when we are converting into cyclohexyl chair form. Okay, this CH3, we are putting CH3 here. This is CH3, and 1, 2, 3, 1, 3. These are trans to each other. So this CH3 and this Cl are trans to each other. 1, 3, 1, 2, 3, 4. 1, 3 cyclohexyl in chair form. We know that 1, 3 axial equatorial is trans to each other. So these are trans, and CH3 and isopropyl rings are trans to each other, and 1, 4 AA axial is transformed. So this is the isopropyl ring. We know that this is less stable one. Okay, this is less stable one, and this ring flips for more stable conformation. That is, ring flips like this. This one, and this is the axial one, becomes equatorial here, CH3, and the next here is a equatorial Cl, it becomes axial, and here is a isopropyl group, becomes equatorial, and this is a stable conformation of chair conformation of this compound neomethyl chloride, and here is an axial chlorine, and here is axial hydrogen, here also one of the axial hydrogens. So it eliminates by ethoxide. That means sodium ethoxide is the base. It can abstract this proton or this proton and gives, if it abstract this proton, the product will be like this. It's a cyclohexane ring. Okay, CH3 is here, and here the isopropyl group, and it is the groups H and Cl, eliminating group eliminates from this position between the cyclohexyl and this one, sorry, so isopropyl and this one. So the double bond is here, that means this one. This is the more stable product. Plus, if eliminate this hydrogen and this chlorine, the double bond is here, that is the product is this one, CH3 isopropyl group, double bond is here. This is a less stable one and this is a stable one. So this is 3:1. The proportion is 3:1. This will be the explanation for this neomethyl chloride. And what about methyl chloride? This is the methyl chloride, CH3 isopropyl group. This is the chlorine here. So convert it to this chair form, and similarly CH3 is here, and these are cis to each other. 1,3 cis is 1,3 cis is one axial, this one axial, so chlorine is here. Okay, chlorine is in this position, that means this in this carbon chlorine. And next in the 1, 2, 3, 4 fourth position, there is a isopropyl group. This is trans to each other, so 1,4 AA is trans, so isopropyl group. We know that this axial one, okay, but this conformer is less stable because this bulkier isopropyl groups in axial position. So this is a less stable conformation, and if it is undergo elimination reactions, the product is like this CH3 isopropyl group and this one. That means here only one of the axial hydrogen is here in the neighboring carbon, that means this hydrogen. So double bond is formed between these two carbons, that is these two carbons. No axial hydrogen is here, but this is not a stable conformation. It flips like this. It flips like this, that is CH3 comes here, CH3, and third position Cl comes here, and the isopropyl groups comes here. This is a stable conformation of methyl chloride, but here no axial chlorine, so no elimination takes place here. No elimination because no axial chlorine. But here is an axial chlorine, but is a disfavored conformation. This is not favored, a disfavored conformation. But if you give the product, it's a slowest reaction because it's a disfavored conformation. It gives the product like this. It's a 250 times slower, but this is the favored conformation. This is a favored one, but here no axial chlorine. So that's about the cyclohexyl E2 elimination, that means the methyl chloride and neomethyl chloride. Next, this one, the E2 elimination from vinyl halides. Okay, this is a vinyl halide, so bromine is here, so double bond is here. This on reaction with LDA, this LDA gives the enalkyne as the product. And this compound, if it is this one R1 BRH R2, this is Z alkene, okay, Z1. So this is first preference, second preference, this goes first preference and this goes second preference. So this one is Z. On reaction with LDA, it gives the product like this, and here the CH bond and the CBr bond, that's our anti-periplanar, so it's a fast reaction. And similarly, if it is like this, R dash, Br and HR2, this is a E alkene, the E form, here is a E form, and also gives this product, but it's a slow reaction because these two, the eliminating groups are cis to each other, they are syn to each other. So here syn elimination takes place, slow reaction, here anti-elimination takes place, the first reaction. This is the E2 elimination from vinyl halides. This is all about the stereochemistry mechanism, then examples of E2 elimination reactions. So we can now conclude this E2 reactions. Thank you.